So we'll zoom out to, that's a good scale right there. And if we look at one of these particular nodes, that one's at elevation 798 feet. It has a base demand of 12 gallons per minute. Keep that elevation in your head, 798. And if we move to the south, if it'll let me move south, there we go. Pick one of these nodes on the south. We're at elevation 810, so it's going up if we move south. Pick one of these other ones down here in this corner. That's elevation 820. So we've gone up 20 feet in elevation by going from the north to the south side of the simulated area. And I'm pretty sure water supply comes from this reservoir, which is at 985 feet. So there's enough elevation. And it connects into, there's almost 200 feet of available water supply head. And then if we move off to the east side of the model, that's also at elevation 785. And some of these pipes are easily a quarter-mile long. So that's a fairly complicated system. So if we were to render the map in terms of elevations, it looks fairly flat. Put the heads in the system. There's nothing to do there, and we're going to run it in a second. Let's check options times. It's currently set up for just a single simulation. I'll make sure it has patterns in it. It does have a variable time pattern in it. That pattern ought to look familiar to you because we've used it elsewhere. If we run it as a single steady state, not much to see in the output because it's very dense, but let's turn the nodes from head to pressure because that's usually of more importance. And now we see an interesting story. In Texas, pressures less than 35 psi violate the expected required pressure in the system, and everything that's yellow or red is below 35 psi. And so we see there's an awful lot of the entire network that doesn't have sufficient pressure. Pretty much everything to the east of this line right there is in violation. You can see we have some negative pressures, in fact. So if that were our initial case, then we would want to adapt. We would use our hydraulic design to try to eliminate these reds and yellows. I'm not going to do that. I'll just run it with the variable pattern. Let me see if I remember how to do that. I do edit, select all, edit, group edit, junctions, demand pattern, (393) junctions. That's a little bit bigger than our 6s and 8s that we've been dealing with. And we also need to turn time on. So we'll run it for 24 hours, although I think it'll fail at hour 16. But we'll see. Ooh, hour 5. But we'll go ahead and let it simulate behavior. So you can see the pressure's all going negative. Okay, just for fun, what would be your first inclination, pretending you could change anything? What would be a logical change to keep these pressures from going into the red zone? And if I can scroll up, I'll... So what?
Pressure is negative, as you said.
It's red. It's below the permitted level.
Yes, second you said to ecological change.
So a logical change would be if we had more head at this reservoir, we should be able to meet those demands. So let's just change this from 985 to 1400. Add a whole lot of elevation. Now that's not realistic. You can't take a reservoir and lift it 300 feet in the air and have it work. But as far as the computer program's concerned, it doesn't care. So I've made that change, and now let me rerun my model. Okay, it's still having problems. Ooh, but I made it to 1800 hours. So keep in mind, yellow and red are undesirable pressures. And if we let it start to show the time simulation, we're still okay. And now we start. We only have a couple hours of low pressures. So for silliness, let's go ahead and just increase this again. Be nice if it would actually accept input. Okay, now I've put in a value that should produce desirable situations. And let's make our lives easier. I'm going to mess, that's not what I want to do. I'm just going to mess with the color scheme. So view, node legends. If I click on it, it goes away, so it's got to be, I want everything else to stay green. We're doing a very binary differentiation here. Okay, so now if it's below 35 psi, it'll show up as red, and if it's above, it'll show up as green. Okay, so there's our system right there. And what's this minus guy right here? Oh, those were flows. We'll turn those off for a time being. Okay, so there's our system. It's green everywhere. And if we let time evolve, I guess my color choice wasn't that brilliant, but we got one moment of red. So we'll go find that next time it occurs. Let's pick one of these locations, and then you were asking how to do a plot. So you select the object, then we grab the graph.
First of all, selecting object.
And press the okie dokie button. And sure enough, the pressure drops below 35 psi for that one moment in time. And actually everything to the south does, and then there's some up in here. Let's just look at what these look like. Same kind of behavior. All right, let me make a quick change to something. I will add another 200 feet ahead. Now, again, you couldn't.
It is 2000. It was more.
You couldn't do this in real case. You can't just start lifting reservoirs up in the air. But what you can do instead is install pump stations.
Yeah.
Okay, now I don't think I'll get any red, I hope.
In that region.
Yeah, so it stayed green everywhere, and we can pick one of those offending locations, which I think was down here somewhere. Plot that, and it stays high enough. So that's a complicated situation. And I don't think I have a water quality on this one. I don't think quality is actually plotted. Yeah, it's not doing any water quality features, but if I wanted to keep track of chlorination, then you would put those features in. You could keep track of it that way. Okay, that takes care of that example. Now let's access the toolkit. So we'll do that next, and
Yeah.
we'll just start working through some examples that are in the notes, because it's illustrated fairly there. Okay, so let me.
That is not working. This notebook is not working.
It's not talking to the Wi-Fi.
Oy.
So I can write on it all we want,
No problem.
but I can't get you the file.
Yeah.
I'll do that. Maybe I can get it to work back at the Noli again.
Yes.
Okay, so
At least we can write.
notebook, small grid, give it a name. Okay, so let me redraw my picture. That's what we're doing right now. Okay, we're here. Finland, Lubbock, Texas. 13, 7 and 7 is for about 7,000 miles. About. And we'll just work through some examples. Okay, I don't need this anymore because so disconnect from that. I will throw it away. Probably don't need this either. I do need to get to the notebook. There we go. So we're in Programmer's Toolkit. So what the toolkit is its formal definition. It's an applications programming interface to facilitate analysis and simulation of water distribution. It contains some essential functions that allow you to directly access EPANet models. And its primary purpose is to enhance EPANet and enable users to access it as part of a computer program rather than what we've been doing, which is using it as part of a graphics program. So what we've been doing is we open the EPANet graphing program and then access the actual computation engine. Instead, we're now going to directly connect to things. So if you were to do this onto a Raspberry Pi, you have to download the source files. You have to build something called a shared object library. Then you would copy the library into a working directory. And then
which page it is?
And we're down right about there. I'm just going to go through the steps. you don't have Raspberry Pi, you can't do it, but it would be very similar to what you do in Windows. So the key things is once the shared object library, or in your case the DLLs, exist on your machine, then you write and run programs to access those scripts. The next part of my notes shows step-by-step how to build a shared object library with the destination machine being a Raspberry Pi. We won't go through that, but it goes through the steps that you would do. So if you do this in the future, it has the most important part are the commands. You would make a directory for the build, you'd change in the directory, you'd run the CMake utility, and then it goes through compilation steps.
Is this for window interface, you mean?
No, this is for a Linux.
This is what I was trying to do. Yeah.
So for Windows, there's a similar but different procedure. I don't have it worked out.
Yeah.
You really need to teach yourself Linux.
Yeah. No, I have done Linux, but the problem is I can get Ubuntu online. What is called? Then it is possible. Ubuntu.
After you've built the shared object library, in my case it ends up in the library directory, and then you either can put a symlink into the path variable or copy the library to where you want to work it. I chose the second one, to copy it. Okay, so the module, EPA module.python, you can get from GitHub. Oh, I didn't know I did a direct link. So here's the GitHub. There's EPANet, the development, real-time extensions, Python module, and EPANet Python. This is what I'm using right now. We're using EPANet Python. And if you were looking at, it would say we can't get there, so you'd have to manually navigate to it. And I just lost everything. Free swim. Okay, so I'll connect to my computer in a second, and we'll actually run through these step by step. So my computer is at address 75.384.227. Open up a Jupyter Hub connection. We've got to wait a second, or two, or three, or four. Oh, I bet it's pulling that I bet it's not hooked to the internet right now. Yeah. Okay, how do I get it to let me log in again? There we go. right about there. So if I log into my computer, I want to make sure I don't do this in the, I guess I can do it in the notes. We'll need that Python module open, close that. Let's create a new notebook. We'll need to name this. What do you want to name it?
ICT Summer School. ICT 2000. ICT, yeah, ICT Summer School 2023.
Okay, so there's our notebook. Let's go back to our examples. We want to check out a particular directory, and we're looking for a directory that contains this Python module. We need that, and we're looking for this shared object module. So to list a directory, I can either go pretty sure this is the directory I'm in. So lesson 3 has the shared object and the Python module. And I think ICT Summer School is also there. Yeah, there it is. So it's all the same directory. So you could do it that way, or if you want to do it in the notebook, let me leave a message for you. I'm not sure if you're familiar with Jupyter notebooks or not. If you're not, these are not. So that's a compute cell. And then this symbol, let's see. Zipit refused to file split cell. Oh, it's got no kernel. If I have to do a remote reboot, I'm going to be kind of angry. Okay, so it still looks like it's moving. Yay. There we go. So everything, the structures, everything is in cells, and the cells are either a markdown cell, a computation cell, there's something called raw, which is it just stores stuff, doesn't do anything. So if I send this command, the exclamation point ls-la, that's going to list the contents of its local directory, and it's the same as the one we already just saw. Okay, so we're in the right place. Let's make our first Python program. Looks like I have example 1. I have example 3 there already, so we'll actually write a Python program in example 3. So using the toolkit guideline, we want to import the package. So to do that, in a computation cell, we type keyword import, the name of the module, and then this part is doing a technique called aliasing. It's allowing us to associate the keyword EM with the module name EPA module. It saves a lot of typing.
Yeah.
So that imports the package. Next, let's run a complete simulation. See, it's all in the same. Just take that part of the comment out. Okay, so we import the package, then we'll run the EPANet model. Only in our case, we're going to do example 3 -tk. And it's EX3 TK. And we'll send it to a report called junk. Okay, that would run the simulation. And then if we want to look at the contents of the report, what do we have to do?
Some command like.
So we have to have it print the contents, and this will do the job. Cat.
Yeah.
All right, everything being equal, this should run the EPANet on our behalf. So a little bit more interaction than opening up a Windows program and clicking on hamburgers and French fries and stuff. Okay, couldn't find INP.
And yours.
Oh, wrong file name. There we go. So it ran the program for us. Okay, that's all it did, is it ran the program for us. In and of itself, so what? You can run the program, big deal. Where the power comes in is we can start changing contents of the program. So let's modify exactly what we did, only now we're going to do it in much smaller chunks. Okay, so I'm going to do a little bit of shenanigans because I don't want to type. Now let's look at what's going to happen, and then we'll go ahead and run it. It's going to open a connection to the file. It's going to also open a connection to a report file. Then we're going to open the hydraulic model. Then we're going to tell it to solve the hydraulic model. Then we're going to save the results. Then we're going to close the hydraulic model. Then we're going to open the quality model, solve the quality, generate a report, and then close everything. So hydraulics, save to binary, quality, generate report, done. So it's the same as before, it's just more step by step. And what will happen, notice the timestamp here, this should be like 7:15 or something when I run it. Well, good guess on my part, 7:14. As far as it looks to us, the output looks unchanged, except for the timestamp, but we've just run the program in a much different way. We ran it one piece at a time. In fact, since this particular program doesn't have any quality associated with it, we could turn off the quality model entirely, run it, and still runs. Let's stop there. Let me stop the recording.